Okay, on the next chapter, chapter 10, talking about bonding. So, here shows the three main types of bonding. We have ionic bonding, where one atom gives electrons to the other atom, and then they're combined by the Coulombic attraction between the ions. Here's covalent bonding, where you have sharing of electrons within a molecule. A molecule is a stable group of atoms. So think of a stable couple. Stable couples stay together. Unstable couples, when you see them, they fight and they break apart. That's an unstable molecule. It fights, it blows up, just like people. And then here's metallic bonding. You have a sea of electrons between nuclei. And I mentioned the Coulombic force before. That's what's uh, keeping an atom together. The electrons attached to the nucleus, and also what keeps a molecule together. Okay, so let's start out about talking about lattice energies. So imagine we have something like a sodium chloride crystal, and what is the energy of taking all those ions and putting them together? This is called the lattice energy, and although we don't measure it exactly, we can get it using what's called the Born-Haber cycle. And here is the Born-Haber cycle. So you start off here. So you have the reactants, sodium plus 1/2 of a chlorine, 1/2 of a mole of chlorine gas. And we don't know the lattice energy. Lattice energy is this step, but we know all the other steps. What steps do we know? We know the overall reaction because we've measured it. And we know so here we go from sodium to sodium vapor. So we know the energy it takes to make sodium vapor. We know the energy it takes to rip apart chlorine. And we know the ionization energy of sodium. And we also know the electron affinity of chlorine. So what we can do is, instead of measuring this directly, we can do step number 5, this 5 here, and begin to say step 5 is equal to the delta H minus 1, minus 2, minus 3, minus 4. Let me get the lattice energy. So, and this is what we've discovered with trends in lattice energies. So if you look here, for the length between the halide chlorides, halide, yes, the alkali chlorides, you can see that for size. So lithium is a tiny ion, cesium is a big ion. As you go down, the size of the atom gets bigger, the bond length gets bigger, and what happens? The lattice energy goes down. This makes sense because Coulomb's law here, the size of the force is over r squared. So smaller r means stronger force. Likewise, the effect of charge 1, charge 2. And if you look at, here's sodium fluoride and here's calcium oxide, and they're about the same size. But if you look at this, sodium fluoride versus calcium oxide, it's roughly 4 times stronger, right? 900 times 4 is 3,600. So, and that's exactly what we expect because the charge is double, so it's Q1, Q2, plus 1, minus 1 versus plus 2, minus 2. You'd expect to be about 4 times. Why isn't that exactly 4? Well, because calcium oxide is a little bigger, so it goes down. It's a little under 4 times, but it's about 4 times, so that fits. So, and the other point of this, the two of these, the more important thing is charge. Charge has a more profound effect than size. So let's do this. Let's arrange this in order of increasing magnitude of lattice energy. So calcium oxide, this is going to be plus 2, minus 2, potassium bromide, plus 1, minus 1, potassium chloride, plus 1, minus, strontium is plus 2, minus 2. So now, so with the sizes, we know that, so increasing. So it's increasing. So the small ones, because of the charge, KBr and KCl, and the big ones are going to be calcium oxide and strontium oxide. So, um, so now we're going to see the difference between KBr and KCl. So potassium is the same. Bromine, though, so you look at the periodic table. Bromine is here, chlorine is here. Bromine is bigger. So this one here is a bigger ion. And likewise, calcium and strontium. Strontium is lower, so it's going to be bigger. So here's calcium and strontium. Calcium is higher, it's a smaller. So the smaller charge is going to be the smallest and the bigger ion. So potassium bromide is the smallest, and that's going to be smaller than KCl. And then the next biggest is going to be strontium oxide, and the strongest lattice energy is calcium oxide. So order of increasing magnitude of lattice energy, it's going to be KBr, KCl, SRO, calcium oxide. And again, the reason for this is that the potassium bromide, potassium chloride are +1, -1, so those are going to have lowest lattice energies versus the +2, -2 of the oxides. And we put bromine as first because it's the bigger ion, it's going to be the smallest lattice energy, and strontium is lower energy than calcium because it's bigger. Okay, see if you can follow which one of these has the highest lattice energy. And this is +1, -1, +3, -2, +4, -4, +1, -3. Which one is the highest? It's the tungsten carbide. Tungsten carbide is a very, very robust compound. It is used to line the inside of the tokamak fusion generators because it's so tough. And people make rings out of this stuff. If you have a tungsten carbide ring, it's wonderful, it doesn't scratch very easily. But be careful with them. They are so strong, they cannot be cut with the jaws of life. So if you have one, you could lose fingers and or hands and arms if you get stuck somewhere, because it's hard to reach and cut the ring. So be careful if you wear them. Okay, so let's talk a little bit about some ionic compounds and what we use them for. So silver nitrate, this is used as an anti-infective agent, especially in infants. We also have Band-Aids that have silver in it. So silver in general is great for killing bacteria. So some people have hypothesized that we'll use silver underwear for people that go into space because that helps kill things. They've already seen it like for hiking, and deployed soldiers sometimes put silver fibers in their undergarments to keep certain areas of the body cleaner for longer because of that. Barium sulfate, contrasting agent for CT scans. I've had this done before. This stuff tastes terrible. Even if they flavor it like crazy, it still tastes terrible. Calcium sulfate used to be used to make plaster casts. Now we typically either use air casts or we use fiberglass. But you can use plaster in art class as well. It's used to do various things, like when you make investments for sculptures, in instance. Potassium permanganate, very purpley stuff. Can use to purify water, not listed here. Great for severe fungal infections like trench foot. Potassium permanganate turns everything purple, like I said. Potassium iodide can kill things, and also radiation sickness. This is only for certain type of radiation sickness. This would be from a plant meltdown, nuclear plant meltdown, or an atomic weapon. So a dirty bomb wouldn't really work for this, but an atomic weapon, one that has a explosion. We have stockpiles of potassium iodide. You take this to help prevent a specific type of radiation sickness. Lithium carbonate, this was the old school antidepressant used to treat specific types of bipolar disorder. A song by the old band Nirvana. Man, I'm starting to feel old talking about these videos. Jeez. Magnesium sulfate, that's Epsom salts, and can be used to treat eclampsia. And magnesium hydroxide antacid and a laxative. Magnesium sulfate is also a laxative. So magnesium salts in general are laxatives. Sodium bicarbonate, also known as baking soda, you can use to treat heartburn. Usually don't anymore. Usually use magnesium hydroxide or calcium carbonate, and it can be used to treat acidosis. Sodium fluoride used to strengthen teeth. It's in toothpaste as well. Tin fluoride is also in some toothpastes. Zinc oxide, this and titanium dioxide can be used as a sunblock. So you can use this as a mineral sunblock to completely block light from the sun. Okay, and I showed these before in the last chapter, but I want to show them again. Here's Lewis dot structure. So Lewis thought that atoms were like blocks. So he thought that atoms were like boxes, like cubes, and there are 8 corners on a cube, and therefore that's what they were built up like this. He was right about the number 8, wrong about the cubes. But that was one of the classic examples of getting the right answer, but for the wrong reason. But number 8 is important because the number 8 is the valence electron shell of the noble gases. And that's also known as the octet rule. With the exception of helium, it just wants 2. So hydrogen and helium just want 2 valence. And but okay, so fluorine has 7 valence electrons. It has 9 overall, so 2 of them are core, but 7 valence, and it's missing 1. So it can combine with another fluorine, and it shares 2 electrons. So now they go into a mutual beneficial sharing situation, and they both have a complete octet, and they bond that way, and that is a single bond. Oxygen has 6 valence, it wants 8, so it can share 2 electrons with its neighbor or its friendly oxygen atom, and it will share 4 electrons or have a double bond. Likewise, nitrogen has 5, it wants 8, it can save 3 and have a triple bond. So before we get into bonding, let's talk about something called electronegativity. Electronegativity is very similar to first ionization energy. The trend is up and to the right is more positive. So the noble gases are not given electronegativities, although xenon does have a positive, or whatever, negative. It really has an exothermic electron affinity. But you can see here that a general trend is, especially for the S and P blocks, are that the up and to the right are the higher electronegativity, and that is the ability of an atom to draw electron density to itself. So it's kind of like if you ever go out and you go to something like Halloween. So if you go to see Halloween, sometimes there's someone who's really attractive out on the street, and you just see like a ring of people that kind of form around these people that are attractive, and you're like, wow, look at this person, I'm gonna get a closer look, and you're drawn towards that person. That's the same thing with electron density, but the idea is, so if you look at fluorine is a tiny atom with a +7 center. So the electron's like, ooh, very tiny, I can get really close to this very strong charge, so I'm very heavily drawn towards it. And then you have an atom like cesium that's a very large atom with a +1 charge. It's not very good at holding on to its electron. The electron, it's like, you want my electron? Take it. Just take the electron. It just pops right off. And it'll go right to fluorine. And it'll surround fluorine. In a bond, though, which we'll talk about, so like if hydrogen bonded with fluorine, they share electrons, but electrons are not dots. They're kind of a fuzzy cloud. The electrons will be shared unequally, and we call this a polar bond. So, and with electronegativity differences, so you can see here, different small, intermediate, large. I personally don't agree with this, but I'm going to teach it anyways. In my opinion, if it's 2 different atoms, it's a polar covalent bond. But The reason why we have this is because organic chemists, they consider the hydrogen-carbon bond to be completely covalent, but it's not. But anyways, uh, this is leading into organic chemistry. And if you have a very large um, difference in it, you can have an ionic bond. And this is also not necessarily true. You can have like oxygen can covalently bond on the surface of platinum, for instance. So this is not true, but it's in the book. One of my philosophies on teaching is I don't like telling you half truths. I'd rather tell you the whole truth. Okay, so a covalent bond is that it's nonpolar. The electrons are shared equally. If it's a polar covalent bond, the electrons are shared unequally. Ionic bonds, there is a transfer of electrons. And here is a picture. Sometimes this is referred to as a blanket thief. So you can see here is hydrogen chloride. So, and it's like if you ever shared a bed with someone and that person is a major blanket thief. You can see here, hydrogen is chilly. It's got a little bit, the little corner of the blanket is covering it. Chlorine is all sitting there happy and warm and all that electron density. That's what's happening here is the electrons around hydrogen, they're being shared with chlorine, but the electron's like, okay, well, I can hang out with this +1 center nucleus, or we have this +7 center nucleus over here. I'm going to spend, and I'm an electron, so I can shift my density and be in two places at once. I'm going to spend more time around chlorine. So the electrons are being shared unequally towards chlorine. And then because of the electrons are not shared equally, there is a partial positive charge on the hydrogen because it's losing electron density, and there's a partial negative charge around chlorine because it has extra electron density. And by partial, I mean less than 1.6 times 10 to the minus 19 coulombs. That's a charge of a electron and proton, respectively, right? So, and then later on in future chapters, we will talk about polar molecules, because you can have a polar bond and still have a nonpolar molecule. The whole entire molecule can be polar. That's coming up in the next chapter, but we still have some more chapter 9 to cover, which we will cover in the next section.